Welcome to Learn with us. This is the 22nd lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you understood what is voltage gain. You also studied about methods for AC modeling. In your last lecture, you also understood what is hybrid pi model with the help of some examples. Now, what are the learning objectives of this lecture? In this lecture, you will understand AC modeling using T model with the help of some examples. Now we will understand AC modeling using T model. We know that the symbol of NPN transistor is like this, where the arrow is here. This terminal is collector, this is base, and this is emitter. Now its equivalent T model circuit will look like this. Now this terminal is emitter. Here we have base. This is collector where this current source is present and the arrow is downward here. Now this is the direction of collector current. This is the direction of base current. This is RE and this is the direction of emitter current and this is alpha IE. Okay. Now what about PNP transistor? We know that the symbol of PNP transistor is like this, where the arrow is here. Now this terminal is emitter, this is base, and this is collector. So its equivalent T model circuit will look like this, where now this current source is here. Now this terminal is collector, this arrow is upward, this is RE, this terminal is emitter, this is base. Now this is the direction of base current, this is the direction of collector current. Here we have alpha IE and this is the direction of emitter current. So these are your equivalent T model circuits for NPN and PNP transistors. Now look at this example. If you have a transistor configuration like this, where now the arrow is here, it means it is a PNP transistor. Now here we have base and for suppose it is grounded. Okay. Now here we have supply voltage of emitter and for suppose it is 10 volts. This is RE and it is of 10 kilo ohms. Here we have RC and it is of 5 kilo ohms. And here we have supply voltage of collector and for suppose it is minus 10 volts. Now here this VBB is 0 volts because it is grounded. Okay. Now if we have an AC source here which is VI and if we have a capacitor here, okay, so how you are going to start your analysis? First we will do DC analysis of this circuit. Now we know that for DC analysis all AC sources are short circuited and capacitor is open circuited. So for DC analysis this configuration will look like this. Okay, here we have VEE, this is RE This is RC, arrow is here. This is VBB, this is VCC. Now we know that this is the direction of emitter current and this is the direction of collector current, and here we have this AC source which is short circuited. Okay, now what we are going to do, first we will find nodal voltage of emitter VE. We know that in PNP transistor at emitter base junction we have voltage drop VEB, which is equal to VE minus VB. In forward biased condition, this VEB is approximately equal to 0.7 volts. Now here as you can see this base is grounded, it means here this nodal voltage of base is 0 volts. It means here we write 0 volts. Now it means this VE is 0.7 volts. Okay. Now we will find terminal current IE. We know that IE is equal to VEE minus VE divided by RE. This VE will be here. Okay. Now we know that this VEE is 10 volts. This VE is 0.7 volts and RE is 10 kilo ohms. Okay. After solving this, you will get 0.93 milliamperes. Okay. Now for suppose here beta is 100, it means alpha is equal to beta divided by 1 plus beta, which is equal to 100 divided by 101, and if you solve this you will get 0.99. Now we will find collector current IC. We know that IC is equal to alpha IE. Here this alpha is 0.99 and IE is 0.93 milliamperes. After solving this, you will get IC is equal to 0.92 milliamperes. Now what about base current? Base current is 0 amperes here, because as you can see here this VB and this VBB, they are at same potential. It means there will be no current flow here. Now what about nodal voltage at collector? We know that VC will be here. It means here collector current is equal to VC minus VCC divided by RC. It means VC will be equal to VCC plus IC RC. Here we know that this VCC is minus 10 volts. This IC is 0.92 milliamperes and this RC is 5 kilo ohms. After solving this, you will get VC is equal to minus 5.4 volts. Okay. Here in this case, VE is found to be 0.7 volts, VB is 0 volts and VC is minus 5.4 volts. It means here VE is greater than VB and VB is greater than VC. It means this PNP transistor is in inductive mode here. Now we will do AC analysis of this circuit using T model. The equivalent T model circuit of this configuration will look like this, okay, and the arrow will be here because we know that this is a PNP transistor. Now here we have this RE, this is RE, this is RC, okay, and here we will have this AC source. Now this is grounded because we know that for AC analysis all DC sources are grounded, and here this capacitor is short circuited. Okay, now here we have VB. Okay, now this is alpha IE, which is equal to IC. Okay, now this is the direction of small signal emitter current, and this is the direction of small signal collector current here. Okay, now first we will find transconductance here. We know that transconductance is equal to collector current divided by thermal voltage. Here collector current is 0.92 milliamperes, and we know that thermal voltage is 0.025 volts. It means transconductance is equal to 0.0368 amperes per volts. Okay, now we will find RE. We know that RE is equal to alpha divided by transconductance. Here alpha is 0.99 and this transconductance is 0.0368 amperes per volts. After solving this, you will get RE is equal to 26.9 ohms. Okay, now we will find R pi. We know that R pi is equal to beta divided by transconductance. Here beta is 100 and transconductance is 0.0368 amperes per volt. After solving this, you will get R pi is equal to 2.7 kilo ohms. Okay, now we will find voltage gain. We know that voltage gain is equal to output voltage divided by input voltage. Here this input voltage is here and output voltage is here. Okay, so as you can see here in this region, VI will be equal to minus IE RE. Why? This negative sign is here because as you can see this direction of emitter current is against these polarities. So this is represented by this negative sign. It means here small signal emitter current will be equal to minus VI RE because we know that voltage in parallel configuration remains same. It means here voltage in this branch and in this branch will also be VI. Okay, now what about output voltage? Since output voltage is here in this terminal, it means here V0 is equal to minus IC RC. Again, this is represented by negative sign here because this direction is against these polarities. Okay. Now we know that IC is equal to alpha IE. Okay. And from this equation A, we know that this IE is equal to minus VI divided by RE, and it is multiplied by RC. It means here this V naught is equal to alpha VI divided by RE, and here we have C. Okay, we can write this equation like this. It is equal to alpha RC divided by RE. Okay, now we know that this is voltage gain AV, so it is equal to alpha RC divided by RE. Now we will put values here. We know that alpha is equal to 0.99, RC is 5 kilo ohms, and this RE is 26.9 ohms. Okay, after solving this, you will get voltage gain which is equal to 184 volts per volts. Okay, so this is your answer. This is how you are going to do AC modeling using T model. Okay. Now look at this example. If you have a transistor configuration like this, where the arrow is here, it means it is a PNP transistor configuration. Okay. Now here we have VEE, and for suppose it is of 5 volts. Here we have RE which is of 3.3 kilo ohms. Okay. Here we have VCC which is minus 5 volts, and for suppose here we have an AC source which is VI, and here we have a capacitor which is connected to a resistor RL which is of 1 kilo ohms. Okay, so how you are going to start your analysis? This is RB, and for suppose it is 100 kilo ohms. Okay, first we will do DC analysis of this circuit, and for DC analysis we know that all AC sources are short circuited and all capacitors they are open circuited. It means for DC analysis this circuit will look like this. Okay, where now this AC source is short circuited. Here we have VEE, here we have RE. This is the direction of IE, this is RB, this is the direction of IB, this is VCC. Okay. Now first we will find base current IB, and for this we will apply KVL in this region, and we start from this point. We know that this arrow means this RE is connected to the positive terminal of this VEE, and this is the negative terminal. And if we start from this point, our KVL equation will be minus 5 volts plus IE RE plus, we know that in this region we have voltage drop VEB, so we will write plus VEB and plus IB RB is equal to 0. Okay, now we know that this VEB is 0.7 volts, and we know what are the values of RE and RB. So this equation will become something like this. This is 3.3 kilo ohms. This VEB is 0.7 volts plus IB. This RB is 100 kilo ohms is equal to 0. Okay. Now we know that IC is equal to alpha IE, and this alpha is beta divided by 1 plus beta IE. Okay. It means IC is equal to beta divided by 1 plus beta IE. Okay. Now we know that IC is equal to beta IB. Now if we compare these two equations, we get beta 1 plus beta IE is equal to beta IB. This beta is going to cancel this beta. It means IE is equal to 1 plus beta IB. And for suppose here this beta is 120. It means here we can write this IE as 121 IB. Okay, 3.3 kilo ohms. Here we have 0.7 volts plus IB 100 kilo ohms is equal to 0. Okay. Now if we solve this equation, we get minus 4.3 plus 499.3 K IB is equal to 0. It means IB is equal to 4.3 divided by 499.3 kilo ohms. Okay, this is volts, and after solving this you will get IB is equal to 0.0086 milliamperes. Now we will find IE. We know that IE is equal to 1 plus beta IB. Here beta is 120, so here we have 121, and we know that IB is 0.0086 milliamperes. It means IE is equal to 1.0406 milliamperes. Okay. Now we will find VE. We know that VE is here, and for VE we will use this formula. IE is equal to VEE minus VE divided by RE. It means VE is equal to VEE minus IERE. Here we know that VEE is 5 volts and IE is 1.0406 milliamperes and RE is 3.3 kilo ohms. After solving this, you will get VE is equal to 1.57 volts. Okay. Now we will find VB. We know that VEB is equal to VE minus VB. It means VB is equal to VE minus VEB. Here this VE is 1.7 volts and VEB is 0.7 volts. It means VB is equal to 0.87 volts. Now what about VC? We know that VB is here and VC is here, we have VE here. Okay. Now what about VC? We know that here VC is equal to VCC plus ICRC, but here we have no RC. It means here VC is equal to VCC, and we know that VCC is minus 5 volts. It means here this VC is equal to minus 5 volts. Okay. Now as you can see here, this VB is greater than VC and VE is greater than VB, and this is a PNP transistor. It means this transistor is in active mode here. Okay. Now we will do AC analysis of this circuit using T model. So the T model equivalent circuit will look like this. Okay. Now here we have current source because this is a PNP transistor configuration. The arrow is here, and here we have RE, here we have this RE, and we know that for AC analysis capacitor is short circuited and all DC sources are grounded. So here we have RL, and this is VI, this is RB, this is IC, which is equal to alpha IE, and this is the direction of small signal emitter current. Okay, so this is your T model equivalent circuit for this PNP transistor. Now we will find transconductance. We know that transconductance is equal to IC divided by VT, and we know that this collector current is equal to beta base current divided by thermal voltage. Here beta is 120 and DC base current is 0.0086 milliamperes, and we know that thermal voltage is 0.025 volts. After solving this, you will get transconductance, which is equal to 0.041 amperes per volts. Now we will find Re. We know that Re is equal to alpha divided by transconductance. Here we don't know the value of alpha, but we know that alpha is equal to beta divided by 1 plus beta. Here beta is 120 and 1 plus beta will be 121, so it will give you 0.99. Okay, now we put this value here. We know that transconductance is 0.041 amperes per volts. It means here Re is equal to 24.146 ohms. Okay. Now we will find voltage gain. We know that voltage gain is equal to output voltage divided by input voltage. We know that input voltage is here and here we have output voltage. Now for input voltage we will apply KVL in this loop, and this would be the direction of our equation. So what will be our equation here? We start from this point. It will be minus Vi plus, we know that here small signal base current is flowing in this direction. So here we have plus IB, RB, and we know that RB is 100 kilo ohms, and the value of this Re is 24.146 146 ohms, and here current is IE, plus we know that this RE and this RL, they are in parallel, so their equivalent circuit R naught is equal to RE multiplied by RL divided by RE plus RL. We know that RE is 3.3 kilo ohms and RL is 1 kilo ohms, and here 3.3 kilo plus 1 kilo. After solving this, you will get R naught 767.4 ohms. So we write here 767.4 ohms, and here current will be IE as well, and it is equal to 0. Okay. Now we know that IB and IE are related. How we know that IE is equal to 1 plus beta IB. It means IB is equal to IE divided by 1 plus beta. Okay. Now we put this value of IB here. So we have minus VI plus IE 100 kilo ohms divided by 1 plus beta plus 24.146 ohms IE plus 767.4 ohms IE is equal to 0. Now IE is common in all three terms. So now we have minus VI plus IE, and here in bracket we will write 100 kilo ohms divided by 121, because we know that beta is 120 here, plus 24.146 ohms plus 767.4 ohms. Okay, so now after solving this, you will get BI is equal to 1618 IE. It means IE is equal to BI divided by 1618. Okay. Now we will find output voltage. We know that output voltage is present here in this region, and since this RE and RL are in parallel configuration, so their equivalent resistance is R naught. Okay, it means here this output voltage is equal to IE multiplied by R naught. Now we know that this IE is equal to VI divided by 1618 ohms, and we know that this R naught is 767.4 ohms. It means here V naught divided by VI is equal to 767.4 ohms divided by 1618 ohms. Okay, after solving this, you will get 0.47. So what is this? This is your voltage gain. Okay, so this is your AC analysis of this circuit. Now here is your class task. If you have a transistor configuration like this, where the arrow is here, it means it is an NPN transistor configuration. Okay, here we have RB, and here you have an AC source. Okay, this is Vi, this is VBB, which is 0 volts, this RB is 10 kilo ohms, this is RC, which is 3 kilo ohms, this is RE, which is 5 kilo ohms, this is VEE, and for suppose it is minus 10 volts, this is VCC, which is 10 volts, and here we have a capacitor which is connected to a load resistor RL. Okay, and you have to do its DC analysis and AC analysis using T model. Okay, now assume here beta is 150. Okay, so this is your class task. That's all for today. Now, what are the key takeaways of this lecture? In this lecture, you understood AC modeling using T model, and you also solved some example problems.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.